The strange part about hypersonic weapons isn't that they're fast. The United States has been building fast things for decades. Intercontinental ballistic missiles already travel faster than anything currently labeled hypersonic. So on paper, the U.S. Navy should be operating in familiar territory. And yet, despite billions of dollars, multiple programs, and years of testing, the Navy still cannot reliably deploy a working hypersonic capability at sea. That's the paradox. This isn't a race against speed. It's a system failing in a domain it's supposedly mastered long ago. At first glance, the problem looks simple. Hypersonic weapons move at Mach 5 and beyond, meaning they travel more than 5 times the speed of sound. At those speeds, reaction time collapses. A missile launched hundreds of kilometers away can reach a naval target in minutes, sometimes seconds. Traditional air defenses, which rely on tracking, predicting trajectories, and intercepting, suddenly face a shrinking window that borders on impossible. The stakes aren't theoretical. Carrier strike groups, the backbone of U.S. naval dominance, were designed around layered defense systems that assume time exists. Hypersonic weapons remove time from the equation. So the expected solution seems obvious. Build your own hypersonic weapons. Match speed with speed. Restore deterrence through parity. And the U.S. has tried exactly that. Programs like Conventional Prompt Strike promise long-range, high-speed strike capabilities launched from submarines and surface ships. On paper, it sounds decisive. If you can hit targets faster than the enemy can respond, you regain control of the battlefield. Except that logic breaks the moment you shift from theory to the ocean. Because here is the problem. Hypersonic weapons are not just fast missiles. They are entire systems that behave differently at every stage of flight. At Mach 5 and above, physics starts rewriting the rules. Air doesn't just flow around the vehicle, it compresses violently, creating extreme heat that can melt conventional materials. Guidance systems struggle because plasma forms around the vehicle, disrupting communications and sensors. Even small errors in trajectory multiply into massive deviations over long distances. This isn't just an engineering upgrade, it's a completely different operating environment. And this is where the equation changes. On land, launching hypersonic weapons is difficult but stable. You control the platform, you control the orientation, you control the environment. At sea, everything moves. Ships pitch, roll, and drift. Submarines operate in constrained geometries. Launch systems must account for constant instability before the weapon even leaves the platform. That instability doesn't just affect launch accuracy, it cascades into the entire flight profile, where precision matters more than ever. But even if you solve launch instability, another layer appears. Hypersonic weapons are only as useful as the targeting systems behind them, and targeting at sea is fundamentally different from targeting on land. Land targets are fixed, ships are not. A carrier group can move dozens of miles between detection and strike. So now you don't just need speed, you need real-time tracking, data fusion, and continuous updates across vast ocean spaces. That requires satellites, sensors, communication networks, and AI-driven prediction models all working perfectly together. And this is where the system starts to fracture. Because that network is vulnerable. Satellites can be jammed or destroyed. Data links can be disrupted. Sensors can be deceived. The faster the weapon, the less time you have to correct mistakes. A hypersonic missile without accurate targeting isn't a precision weapon, it's an expensive guess. And at these speeds, you don't get a second attempt. That sounds like a solvable integration issue, except there's another constraint quietly shaping the entire problem: cost. Hypersonic weapons are extraordinarily expensive, not just to build, but to test, maintain, and deploy. Every test involves complex instrumentation, tracking systems, and risk. Failures are not just setbacks, they are multi-million-dollar losses. This slows iteration. And in modern warfare, speed of iteration often matters more than raw performance. Countries like China have approached the problem differently, emphasizing volume, redundancy, and regional deployment rather than perfect global precision. That changes the strategic balance. And this is where the hidden asymmetry emerges. The U.S. Navy is designed for global power projection. It needs systems that work anywhere, against anyone, under any condition. That requirement multiplies complexity. A hypersonic system that works in a controlled test range isn't enough. It must function across oceans, climates, electronic warfare environments, and unpredictable combat scenarios. Meanwhile, a regional power can optimize for specific theaters, reducing variables and accelerating deployment. What looks like a technological race is actually a difference in constraints. But here is the deeper dilemma. Even if the U.S. Navy successfully deploys hypersonics, it doesn't automatically solve the defensive side of the equation, because defending against hypersonics is arguably harder than building them. Intercepting something moving at Mach 5 or faster requires not just speed, but prediction under uncertainty. You're not just tracking a ballistic arc anymore. Hypersonic glide vehicles can maneuver, change altitude, and exploit gaps in radar coverage. That breaks traditional interception models. So now the Navy faces a dual problem. It must build hypersonic weapons while simultaneously reinventing its entire defensive architecture. And this creates a no-win scenario. If the Navy prioritizes offense, it risks leaving its own fleets vulnerable. If it prioritizes defense, it falls behind in strike capability. Resources, time, and engineering focus are finite. Every decision shifts the balance somewhere else. And unlike previous eras of naval warfare, there is no clear dominant solution emerging yet. So the paradox at the beginning starts to make sense. The U.S. Navy isn't struggling because it lacks speed. It's struggling because hypersonics are not a speed problem. They are a systems problem, a convergence of material science, guidance, networking, platform stability, cost, and strategic doctrine all colliding at once. Solving one layer exposes another. Fixing the weapon doesn't fix the targeting. Fixing the targeting doesn't fix the defense. And fixing the defense doesn't restore the lost time that hypersonics erase. In the end, the real challenge isn't building something that moves faster. It's building a system that can think, adapt, and operate faster than the chaos it creates. And that's the part most people miss. Hypersonic weapons don't just compress distance, they compress decision-making itself. And in a world where decisions break before machines do, speed stops being an advantage and starts becoming a pressure point.